This video will start our series on aldehydes and ketones. So aldehydes and ketones are two pretty similar molecules. They both have this carbonyl, the carbon to oxygen double bond in both aldehydes and ketones. So this is called a carbonyl bond. So we have a carbon double bonded to oxygen. When that carbon is bonded to a hydrogen, this is called an aldehyde. And then when that carbon is bonded to two other carbons, two other R groups, this is a ketone. So R can be a few different groups. It can be an alkyl chain. It can be an aryl group, which is an aromatic ring. In aldehydes, the other R group could be a hydrogen, and that is still an aldehyde. But in a ketone, the R groups cannot be hydrogens, or else that would be an aldehyde. So there are a few groups. We'll see a few examples. Here are two possible R groups that could be in these molecules. So we will have quite a few videos on aldehydes and ketones. This is a key topic in organic chemistry too. And let's look a little bit more in detail about the bonding between the carbon and oxygen here. I'm going to draw the carbon to oxygen bond at a different angle where we're looking at it where one of the single bonds is kind of going away from us and one is coming towards us. So we're looking at it in like a flat orientation where the carbon and oxygen are along, let's say if we have X, Y, and Z plane, carbon and oxygen are along the X plane, the X axis, and then the other two bonds are along the Z, going away from us and coming towards us. This carbon here is an sp2 carbon. It has 3 sigma bonds. So one sigma bond is one of the bonds in the double bond, and then the other 2 single bonds are sigma bonds. So these are overlapping from the carbon sp2 hybridized orbital and the other atom's orbital, oxygen or whatever else is bonded to that carbon. And then there's a pi bond, which I've highlighted in green here, between carbon and oxygen. So we can look at this pi bond in a little bit more detail, where I'll draw the molecule in the same orientation. Now remember, a double bond exists between unhybridized p orbitals. So on both the carbon and the oxygen, there is an unhybridized p orbital. These are overlapping. So here, let me erase that. What I've just drawn here are the atomic unhybridized p orbitals. When we draw the overlap, we did this with diene molecules. This is the molecular orbital for those 2 p orbital overlaps. So we'll talk a little bit more about orbitals in a future video. But this is what the bonding looks like in an aldehyde and a ketone between that carbon and oxygen, where that carbonyl bond exists. Now let's think about the dipole here. We have a carbon to oxygen double bond, this carbonyl bond. Carbon is bonded to 2 other groups where we won't specify that here. We'll keep it general to both aldehydes and ketones. But focusing on that carbon to oxygen bond, oxygen we know is more electronegative than carbon, and so that oxygen pulls electron density away from the carbonyl carbon. So we have carbon that is a little bit electrophilic here because of that oxygen pulling electron density away. We have a partial negative charge on the oxygen and a partial positive charge by the carbon. Now we have a dipole here, which means solutions of only aldehydes or only ketones would have dipole-dipole interactions. But if you have another molecule in solution that is a hydrogen bonding donor, hydrogen bonding intermolecular force, it has a hydrogen bonded to another electronegative atom, then this oxygen in aldehydes and ketones can be a hydrogen bonding acceptor. So that causes aldehydes and ketones to have a higher boiling point than similar nonpolar molecules. Because it has a dipole, but also a lower boiling point than similar molecules that are hydrogen bonding donors. So let's draw what that looks like, where the carbon to oxygen bond, this oxygen can accept hydrogen bonding interactions. So the oxygen has two sets of lone pairs. If there's another molecule like water, we know water can hydrogen bond between water molecules. Well, if a ketone or aldehyde is in the presence of water, that oxygen can accept a hydrogen bonding interaction from another water molecule. Both sets of lone pairs here can accept a hydrogen bonding interaction. But ketones and aldehydes themselves don't have hydrogens bonded to electronegative elements to be hydrogen bonding donors. So water on its own is both a hydrogen bonding acceptor and a donor because it has the hydrogen and the oxygen. Now let's just compare this between some real examples here. So I'll look at 3 molecules and compare the boiling point. So we'll look at similar molecules. Here we have propene. And I'm drawing it in a specific way so we can see the similarities between these molecules. So we have propene. We'll do acetaldehyde, which we'll talk about the naming here. So now we have an aldehyde, and then we'll look at a alcohol similar molecule. And then boiling points. So our first molecule, we don't have any dipoles, all non-bonding interactions. The boiling point we'd expect to be really low. Not a lot of energy is required to disrupt the intermolecular interactions or interactions between molecules of propene. And the boiling point is low. It's negative 47.4 degrees Celsius. For the aldehyde, we'd expect this boiling point to be a little bit higher than the boiling point of propene because we have a dipole interaction now. We have carbon to oxygen double bond that has a dipole. We have a stronger intermolecular force between aldehyde molecules, and that checks out with the boiling point. This is 20.8 degrees Celsius boiling point. And then we have ethanol, which has both hydrogen bonding donor and acceptor abilities. So we'd expect this to have an even higher boiling point, and that is correct. We have 78.3 degrees Celsius. So main takeaway here is that aldehydes and ketones, because they have a carbonyl bond, so going back to the beginning, we have carbonyl bond between carbon and oxygen that exists in p orbitals, unhybridized p orbital overlapping between carbon and oxygen. There is a dipole in the molecule, so we have slightly higher boiling point, but not quite as high as hydrogen bonding molecules.